lab to motion of the falling object. So in this lab, the system was a ball being dropped in the surroundings, which is everything around it, the earth, and the initial conditions were that the object was at rest before being dropped, and we assumed there were no other forces other than gravitational and drag force. So the purpose of this lab was to illustrate Newton's second law, which is that force is equal to the change in momentum per change in time, and that acceleration will only change if there's an unbalanced net force acting on the object. So in this lab, the forces acting on the object, which was a ball, were the gravity force and the drag force, which act in opposite directions. But in this lab, they did not cancel out. The gravitational force was greater, and thus the object accelerated in the downward direction. So these are the physics principles and formulas used. We use the velocity update and position update as we did in the last lab, but in addition, we also use the gravitational force formula and then the drag force formula. So gravitational force. So Newton's first law of inertia states that an object in motion stays in motion unless acted upon by an outside force, and that velocity remains constant if there's no net force acting on the object. And Newton's second law, which came into play in this lab, states that net force determines the acceleration of an object. So in this case, gravitational force and drag force were acting on the ball that was being dropped, and we assume that gravitational force remains constant at negative 9.8 in meters per second, and thus that the acceleration downward is at a constant rate. And to evaluate this, we developed a computational model assuming no drag force, and then we also developed a computational model with drag force and gravitational force. So no drag force means that the only force is gravitational force, which we assume is constant, and therefore the net force would not be zero because it's not balanced, so the acceleration is downward but at a constant rate. With drag force, that means there's gravitational force and drag force acting on the object in opposite directions. So if the forces are equal in magnitude, then the net force on the object is zero, and then there is no acceleration. However, in this experiment, the object was an intermediate between these two models. The drag force was less than the force due to gravity, and it's still accelerated in the downward direction. So to test the motion analysis of the object being dropped, we used tracker, similar to the last lab, which recorded the position, the y position or vertical position as time went on. To develop the computational models, we can see the code here. So to develop the first model, which was just taking into account gravitational force but no drag, we set line 57 to 0 because we were assuming no drag force. And then in line 73, we can see we were taking into account gravitational force. And then in line 71, we have gravitational force formula. 76 is the velocity update formula, and then 78 is the position update formula. And you can see here how the formula is translated to code. Then for the model with drag force, we had the same things as in the previous slide. However, on line 57, we had the drag proportionality constant instead of 0. And this was found through trial and error from the data gotten from the tracker application. And then in line 72, we have the drag formula, which you can see here. And then line 73, which is the net force, now takes into account the drag force in addition to the gravitational force. So these are all the models plotted together. So we can see the yellow is the both drag and gravitational. The red is just gravitational, and the blue is the observed experimental. And we can see that the observed is kind of intermediate between the two. So experimentally, the object traveled down for longer, so it was in the air longer before hitting the ground than in the computational model that had no drag force and was only gravitational force. And the computational model with drag force shows a flatter curve, and it also stops sooner, so it predicts that the object takes longer to travel the same distance and that the acceleration decreases until the drag force equals the weight of the object. And this is based on the assumption that drag is proportional to the square of velocity, and that as velocity increases, drag increases until it equals the weight of the object, thus causing no net force on the object, and then the acceleration equals 0. So possible sources of error in this lab could be an error in the manual entering of the position and tracker per each frame, and then also potential other forces in the room acting on the ball, such as like air conditioning, things like that. So for the what if the object were thrown down, the terminal velocity would be the same as the observed in the drag force model. And this is because initial velocity does not affect terminal velocity. Terminal velocity is when the speed is constant, and that's when drag force and gravitational force are equal. And this is determined by the weight and shape of the object and the surroundings, not by the initial velocity. And then, as mentioned, terminal velocity was predicted by the model with drag. The first model has no drag force, so drag force could not equal gravitational because drag force isn't taken into account, so that wouldn't work. And then when gravitational force is balanced by drag force, the net force is 0 and there's no acceleration, so the object falls at a constant speed.